What specific problem does your proposed method aim to solve within the context of transformer-based large language models? Can you elaborate on the inefficiencies you identified?
The proposed method aims to address the inefficiencies associated with the redundant architectures in transformer-based large language models, LLMs, which complicate their real-world deployment due to inflated costs and resource demands. Specifically, the research identifies that while transformer architectures consist of multiple stacked blocks, each containing distinct MLP and attention layers, there exists a significant level of redundancy, particularly within the attention layers. For instance, the study reveals that dropping up to 50% of the attention layers in models like Llama 2 to 70B results in minimal performance degradation, only 2.4%, while achieving substantial speedup up to 48.4%. This redundancy leads to unnecessary computational and memory costs, especially in the context of the KV cache, which is exacerbated by the autoregressive nature of attention. By proposing techniques like attention drop and joint layer drop, the work systematically reduces these redundancies, thereby enhancing the efficiency of LLMs without compromising their performance.
How does the proposed method work? Please illustrate the process step by step, detailing the significance of the joint layer drop and attention drop techniques.
The proposed method systematically identifies and removes redundant modules in transformer-based large language models, LLMs, through two key techniques, attention drop and joint layer drop. First, a similarity-based metric is employed to assess the importance of each module by measuring the similarity between their inputs and outputs, with lower similarity indicating higher redundancy. The attention drop technique specifically targets attention layers, revealing that a significant portion can be pruned without degrading performance. For instance, dropping 50% of attention layers in Llama 2 to 70B results in only a 2.4% performance reduction while achieving a 48.4% speedup. Building on this, joint layer drop combines the importance scores of both MLP and attention layers, allowing for a more flexible pruning strategy that targets low-importance layers from both types simultaneously. This approach yields better performance under high sparsity conditions compared to pruning only one type of layer, demonstrating that the redundancy in attention layers is a consistent and inherent property of transformer architectures. Overall, these techniques significantly enhance model efficiency by reducing memory and computational costs while maintaining performance.
Can you provide a specific example that demonstrates the application of your method? Walk through the algorithm using a hypothetical model or dataset to clarify the steps involved.
A specific example demonstrating the application of our method can be illustrated using the Llama 2 to 70B model. We begin by employing a similarity-based metric to assess the redundancy of the model's components, particularly focusing on the attention and MLP layers. For instance, we compute the importance scores for each attention layer by measuring the cosine similarity between the input and output, identifying layers with high similarity as redundant. After identifying that we can drop up to 50% of the attention layers without significant performance loss, we implement the joint layer drop algorithm. This approach allows us to simultaneously prune low-importance attention and MLP layers, resulting in a model that maintains over 97.6% of its original performance while achieving a speedup of 1.48 times, demonstrating the effectiveness of our method in optimizing model efficiency.
What are the key theoretical and practical benefits of using your proposed method compared to existing techniques in model compression and redundancy reduction?
The key theoretical benefit of our proposed methods, attention drop and joint layer drop, lies in their targeted approach to redundancy reduction, specifically focusing on the distinct roles of MLP and attention layers within transformer architectures. Unlike existing techniques that apply universal pruning strategies, our methods leverage a similarity-based metric to identify and drop redundant layers, resulting in a more efficient model without significant performance degradation. Practically, our findings demonstrate that dropping up to 50% of attention layers in models like Llama 2 to 70B leads to only a 2.4% performance reduction while achieving a speedup of up to 48.4%, showcasing a superior trade-off between speed and performance. Additionally, the integration of our methods with quantization enhances overall efficiency, making them more suitable for real-world deployment scenarios. Overall, our approach not only reduces memory and computational costs, but also maintains high performance, addressing the inefficiencies associated with traditional model compression techniques.
How was the effectiveness of your method validated in your experiments? Elaborate on the experimental design, datasets, benchmarks, and metrics used to measure performance.
The effectiveness of our methods, particularly attention drop and joint layer drop, was validated through extensive experiments using various models, including Llama 2 to 13B and Llama 2 to 70B. We employed a similarity-based metric to assess the redundancy of MLP and attention layers, which allowed us to compute importance scores for each layer based on the cosine similarity between their inputs and outputs. The performance impact of dropping layers was measured using a new metric called speedup degradation ratio, SDR, which quantifies the trade-off between performance degradation and speedup achieved. We conducted evaluations across multiple datasets, including pre-training and instruction fine-tuning datasets, to ensure robustness, and we tracked the performance across different dropping ratios, revealing that dropping up to 50% of attention layers resulted in minimal performance loss, only 2.4% reduction, while achieving significant speedup up to 48.4%. Additionally, we visualized the importance scores and dropping order of layers to further substantiate our findings, demonstrating that deeper layers exhibited higher redundancy and confirming the inherent properties of attention layers throughout the training process.
What limitations did you encounter with your proposed method, and how might these limitations affect the application of your approach in real-world scenarios?
One limitation encountered with the proposed methods, particularly the block drop and MLP drop, is that they lead to significant performance degradation when entire blocks or multiple MLP layers are removed, especially at higher drop ratios. For instance, dropping 8 blocks resulted in a 7.5% performance drop, indicating that these aggressive pruning techniques may not be suitable for all applications where maintaining performance is critical. Additionally, while attention drop shows promise with minimal performance impact, its effectiveness may vary across different model architectures and tasks, potentially limiting its generalizability. Furthermore, the reliance on a similarity-based metric for assessing redundancy may not capture all nuances of layer importance, which could lead to suboptimal pruning decisions in certain contexts. These limitations suggest that while the methods can enhance efficiency, careful consideration and testing are necessary before deploying them in resource-constrained or performance-sensitive real-world applications.